Okay, good afternoon. I want to present you our results for the additive manufacturing and laser polishing of a pylon bracket out of Inconel 718. And in the project AMAZE, we have been involved in the work package 3, where we developed the process strategy for powder bed, laser M technology with higher deposition rates, and also for laser metal deposition for the powder blown laser technology. And based on these results, we try to manufacture a pylon bracket. In addition, we have also been involved in work package 4. I think Thomas Kosche from BCT presented some results for our laser polishing activities, and the idea was to have a post-processing also if the
Probably a phone somewhere, so if you could switch off, that would be brilliant.
Okay.
I'll take it from you.
Yes, to post-process it by laser polishing. So first, what have been our tasks within this project? First, or objectives, first to demonstrate the potential of high-power SLM process strategy by manufacturing a real component. We wanted to transfer the parameters we find out for high-power selective laser melting with laser powers up to 1.5 kilowatt to produce a real part. Another point is to demonstrate the potential of the high deposition rate for high deposition rate laser metal deposition, so powder blown. Also there we worked with increased laser power and tried to transfer it to a real part. Also laser polishing, which is commercially used to polish molds after the cutting process. We wanted to use it as a post-processing technology for additive manufactured parts. And the last one, which is important, I think, for all industry members, we wanted to evaluate the manufacturing time, because manufacturing time means costs, and we need to know what we could save by using these findings within the AMAZE project. So before we start, I want to describe or show you what part we used. Thanks to Airbus Group at this point. They delivered us a part called pylon bracket. It is located at the A320 Airbus plane and connects the pylon with the engine. You can see it here, and in reality it has a size of approximately 500 millimeters times 60 times 70. So for the high deposition rate LMD, we could manufacture it in the real size. But for the SLM, due to our system we have an SLM 280 from SLM Solutions. We are limited in the space and in the built-in envelope to 280 times 280. We had to reduce it to a size of 272. You can see it here. Okay, then we started first with the powder bed laser AM. We used the so-called skin score strategy. I think David Wimpeny talked about this topic this morning. It can easily be described if you have a look to this cube. If you want to produce it with the skin score strategy, you divide it into an inner core and an outer skin. The outer skin has restrictions for the surface roughness, for the detail resolutions, and so you use a small laser beam, a small surface roughness, approximately 30 micrometers, and you use laser power in the range of 300 watt to process Inconel 718. For the core, and the skin is approximately 1.5 millimeters thick in this case for the pylon bracket. For the core area, you use an increased layer thickness, an increased laser beam to get more energy into the powder bed. The beam diameter is 720 micrometers, and also you have a top head intensity distribution in comparison to a Gaussian intensity distribution for the laser which is used at the skin area. And so you can use 1 or up to 1.5 kilowatt laser power and can increase the process speed by increasing the layer thickness and scan speed. So on the right side you can see the demonstrator, which is cutted in a plane, and I hope you can see it. The red areas are the boundary areas, the skin area, and the gray areas are core area. This can automatically be done with the materialized software to divide it into these two volume areas. Okay, afterwards we manufactured a pylon bracket with a reference and also with 3 different strategies for high power SLM. So first we used 1 kilowatt laser power for the core. Then we increased the layer thickness from 90 to 150 micrometers, and afterwards we built a demonstrator with 1.5 kilowatt laser power. You can see in the picture below the part manufactured with conventional SLM 300 watt, and above with the skins core strategy. From outer side on this picture, I think you can see no big difference. What does this mean for the manufacturing time? You can see it on the right side. We divided it into the primary processing time. It's too easy to say, it's when the laser is on, and the auxiliary time for powder deposition. And what you can see here is that we could reduce the laser on time, the primary manufacturing time, by the use of the high power SLM strategy by 28%. What we have to say is it depends on the geometry you use and you want to build up how much time you can save by use of high power SLM. But this part was not so big and voluminous. So if you think about tooling inserts out of maraging steel, I think with this strategy you can save a lot of more time. But also at this point we could save 28%. Yes, we had a look at the accuracy. You can see here above the reference and down the high power SLM. What we could see is that the high power SLM part has a little bit worse the accuracy, especially at the edges. We have 0.3 millimeters plus minus in comparison to the parameter set for the reference. It's plus minus 0.2 millimeters. Yes, if you process Inconel 718, you always have distortions, and this is not an easy material to process it with powder bed technology. What we could also see for the high power SLM is that we get spatters, which can be observed mainly on the side of the shielding exhaust. I hope you can see that in the picture above, that there are little spatters which also exist, but after post-processing it had no influence on the part properties. Okay, after this we also have a group at Fraunhofer ILT who is doing a redesign, designing and so on. We did a design study. We got some information about the screws connections used for this part, and based on this connection forces we could estimate what load the part has to withstand, and we put it into our topology optimizer. We use Abacus and calculated this part, which can also be seen in the room here in the exhibition. And what we could see, or what we want to demonstrate, is it's not only the process you can save time or money with, it's also the combination of increase the process speed and also adapt the design, because you have to start with the design to fully and complete use the geometrical freedom of this process technology and to increase the process speed. Okay, afterwards we did the post-processing. Therefore we divided the powder bed additive manufactured piling bracket into 3 areas. You can see the right one is the SLM as built. In the middle we use the milling process, and on the left side we automatically did the post-processing by laser polishing, by our laser polishing group. And therefore we used a 2-step polishing process. The first step there are different roughnesses on such a part. Therefore we need a beam diameter of 400 micrometers to reduce the bigger roughness. And in the step 2 we did a fine polishing with a beam diameter of 250 micrometers to get this shiny surfaces you can see here. And how this works, I want to show you in the video. This is the rough polishing. You can see here the machine, it's a 5-axis machine developed at ILT. Does this automatically if you do the scan path programming and calculation. And okay, and then you can see here the fine polishing. It's not that fast as the rough polishing, but you can see that then you get the shiny surface by doing this. You can see the results. We brought a demonstrator with us, and you can see the results also in the exhibition. Okay, what does this mean? Afterwards, we measured the surface roughness, and you can see here that after the SLM process, we had an initial surface roughness of 7 up to 15 micrometers. This depends on the angle between the part geometry and the platform. Overall, the polishing for the two-step takes 22 hours and 38 minutes, but it can be done automatically. So, the surface roughness after laser polishing was then 0.24 up to 0.39 micrometers. So it was significantly reduced by 98 or 99% from the surface roughness we had after the SLM process, and it was also in the same range as the surface roughness after the milling process. So finally, we also, as I said, built up the part by the powder-blown laser AM. You can see it here. To do this, first we had to do a build preparation and NC offline programming to give the laser information what path he has to move on and where he had to deposit material. Due to the limitations of the LMD process, you cannot directly build overhangs. We have to clamp the part in another position. We did two steps. First we had features like these drilling holes. We removed these features because they can be integrated in the part afterwards at the machining, and also this feature added these blue colored features, the fillets. We deposit the powder in the nacelle clamping position afterwards in a second clamping position. So also we manufacture different parts or test specimens to find out what are the right parameters to manufacture this demonstrator by the powder blown process, and we can see that if you increase the track size, that you can significantly increase the deposition rate, but you lose accuracy. And what was also a point, if you increase the track size, you get a lot of energy into the process, and so you have to additionally cool the part, cool it down, and this cooling time reduces the deposition rate, and therefore we had to find a compromise. So we used 2 millimeters track size to manufacture the demonstrator. You can see first we built up half of the demonstrator. You can see it here above, and afterwards we transferred the results to the whole demonstrator. And what we could see is that in the full length of 494 millimeters with a height of 60 and a width of 67 millimeters, we could manufacture this part. It has a weight of approximately 7 kilograms, and a laser spot size of 10 millimeters was used, and a nominal deposition rate of 600 grams per hour for the nickel-based alloy. So before we started in the AMAZE project, a deposition rate of 150 grams per hour was the reference, so we could increase it by a factor of 4. Overall, the manufacturing time, which is divided into the primary body deposition, the cooling time, and the fillet section, so the overhanging section which had to be deposited, and the cooling time took approximately 24 hours. And after manufacturing the demonstrator, we also had a look at the accuracy, and you can see here that in the center we have an accuracy which is between plus minus 1 or 1.5 millimeter. Only at the edges where you can see where it is red shape, there you have an accuracy of plus minus 2 up to 2.5 millimeters. So thank you very much for giving for the presentation and for giving me your attention. And if you have any questions, please ask me. Thank you.
Any questions for Sebastian before we move on?
You say that you're using two general strategy, core and
Skin.
Mm-hmm. But do you use any different scanning strategies, like island or zigzag or any other?
No, it's a stripe scanning strategy. You can you have in the Magic software, which is commercially available. Yes.
So this one. And the second question, you're saying that the polishing with laser polishing is better, gives better results than the milling.
It depends. In this case, yes, but it depends on the milling. If you have a very long milling process, I think you can also achieve very good surfaces.
But possibly here the laser polishing is also here slower.
It is slower. At the moment, it is slower. Yes, but that's a research topic to increase the speed and.
You made a topology optimization of the part. Have you considered into this topology optimization the possibility to go for the laser polishing, or is it only based on the topology optimization?
No, that was an additional work when we started in the AMAZE project. It was not a task to do a topology optimization, but we have a group dealing with the topic, and then we had the idea when we saw the manufacturing time, let us do the topology optimization just in one trial to see what we can save from the weight and what we can save from the manufacturing time. If we would do it the next time, we would integrate more information so that we don't have overhangs, that we have accessibility for laser polishing and so on. These are all informations you need to do a real design which is acceptable for additive manufacturing and also for the post-processing.